All right, we'll go ahead and get started today. This is our Wi-Fi 101 webinar. And this is something we've been doing for a while now. We put this together because we found that, there's a lot of misconceptions with Wi-Fi and just a lot of in general, not understanding why certain things happen, certain problems you run into. So rather than really looking at specific hardware or Zyxel products, for the most part, we're just going to sort of go through the technology, the history of Wi-Fi, sort of explain how it works. Because once you start to be able to understand how it works, it helps you when it comes to, designing new deployments, troubleshooting problems you run into, et cetera. Wi-Fi is, one of those things where, it interacts with the environment, but you can't see it, you can't feel it. So it's sometimes really hard to figure out what's going on. So we'll start with just one quick slide on who Zyxel is for those of you that aren't familiar with us, new partners, people watching on Facebook. So Zyxel's been around for over 30 years. We got started all the way back in 1989. We are a global company. We sell in 150 different markets, and we've deployed over 100 million devices out there in the field. So we'll start by talking about some of the basics. So one of the things you'll look into here is the history of Wi-Fi. And some people are surprised to see that Wi-Fi actually got started all the way back in 1997 with 802.11. A lot of people are only familiar with 802.11a and b, which is when it really first started to take off in the consumer space. But there was a version before that that didn't have any letters tacked on to the end of it. And it is something that Zyxel actually made. We used to sell 802.11 PCMCIA cards to add Wi-Fi to your existing laptop back then, predating 11A and B. And we've been doing Wi-Fi ever since. So 802.11ax or Wi-Fi 6, Wi-Fi 6E, that is the latest technology that's really, truly out there. 802.11be or Wi-Fi 7 is coming. There may be some consumer devices out there already claiming it. And this is something we've seen before when it comes to Wi-Fi, which is before the standard gets ratified, you will find products on the market claiming to be based on that standard that doesn't yet officially exist. That's the case here with Wi-Fi 7. At this point, this standard is locked down enough that most of the chipset vendors have enough to go on to make something that should be compliant. But one of the things we've run into time and time again has been that oftentimes these first generation chips may be missing some of the features that are needed for to fully implement the new standard. So for instance, with 802.11 AC, we had a situation where we had wave 1 and wave 2. With 802.11n, you might remember a lot of products hit the market and they were honest enough back then to call themselves pre-11n. Several of them promised, firmware updates to the full standard, but unfortunately the standard changed enough that in many of those cases, it was not possible to upgrade. The chips just lacked the features needed to truly be 802.11n. So it's something to keep an eye on as we go forward here and Wi-Fi 7 starts to hit the market. Now, there are three big players when it comes to Wi-Fi as far as regulations and standards go. So I wanted to take a second here to talk about them. Oh, also, as we go through today, if you have any questions, send them in using the question and answer interface. And depending on the question, I'll answer it as we go through, or I'll catch it at the end of today's presentation. So the main players here are going to be IEEE. So these are the guys that create the standards. It's a group of engineers in the across the world that create the standards that we use. And this is true for any sort of networking type equipment, whether we're talking Wi-Fi, wired, etc. So they're the guys who create the standard. So when we're looking at that previous slide and you see 802.11b, 802.11, AX, etc., that's a reference to the standard that the IEEE has put out. Now, one of the problems we ran into in the early days of Wi-Fi was that, there's always room for interpretation, and there was no standards body there to clear up any confusion between different vendors on how to interpret certain parts of the rules, and there was no enforcement mechanism to make sure everybody did follow the standard that was there. So that's where the Wi-Fi Alliance came in. The Wi-Fi Alliance is who created the term Wi-Fi. It was a group primarily of manufacturers who got together, who tried to solve these compatibility issues. So you didn't have to worry that your Wi-Fi adapter wasn't going to work with your Asus home router, et cetera, et cetera. So they implemented a certification program that's heavily based on compatibility tests, making sure everybody can talk to each other. So it is not required. It is not a government agency. And in general, you will only see the Wi-Fi certified logo on consumer grade equipment. In general, business equipment doesn't need this, although I'm sure they're using the Wi-Fi test plan as a basis to make sure everything is following what Wi-Fi Alliance wants to see. So they're the ones that decided to rebrand Wi-Fi as Wi-Fi 6, Wi-Fi 7, etc. And then there's the FCC. So this is the federal government. They don't really have anything to do with how Wi-Fi operates from a technology standpoint. What the FCC is concerned with is with radio waves. So Wi-Fi is using radio waves to send and transmit data. So that's where the FCC comes in. So they'll set rules as to which frequencies we're allowed to use. They'll set rules for how much power we can use, rules for how much of your signal can bleed over, whether you need a license or not, etc. Now, for the most part, FCC rules are based on self-certification. The FCC doesn't test our products. Instead, what happens is we go out to an independent third-party lab, we pay them to test and certify the product, and then we take that report and submit it to the FCC. So in general, when using radio waves, you need a license. However, the FCC has unlocked some small areas of space, which is where Wi-Fi operates, that don't need licenses. So we'll talk a little bit here about radio waves. So again, Wi-Fi is using the radio to send its signals. It's no different than, an FM or AM radio or a walkie-talkie or any other sort of wireless device. The only thing that we really have to worry about here is the different frequencies that each of them use. So as a general rule, as the frequency goes up, it becomes easier to cram more data onto it. That's why in the early days, 802.11a was faster than 802.11b. But as the frequency goes up, the range goes down. So for those of you that are old as dirt like me, you might remember the days of home cordless phones. So in the original days, when those were first popularized, they were operating in the 900 megahertz space. So it's a very low frequency. The sound quality wasn't the greatest, but the signal could go really, really far. If you lived in a suburban area, it was very possible that you'd be able to get on the phone at your house and walk across the street to your friend's house and be able to maintain a phone call. In the early 90s, we saw a push to 2.4 gigahertz. So it's a higher frequency. The sound quality got better, but the range became less. And then today, you'll find that most cordless phones are operating in the 5 gigahertz space. And why that is, it'll make more sense in a minute. And again, same thing, a little bit better sound quality, but the range is even worse. So, if you've got a large McMansion, it may be that your cordless phone doesn't actually cover all corners of your house, or that you have sound quality issues in certain parts of your house, versus the old days of 900 megahertz, where you could leave your house and go to someone else's house, and it may very well have still worked. I remember somebody I was dating, their parents actually had a scanner that could pick up 900 megahertz, and they would listen to people's phone calls that were living over a block away from them. So signal went really far. So again, when it comes to radio frequencies, you need to have a license to use and transmit on those frequencies, and that you get from the FCC, and some of those licenses can be ridiculously expensive. Now, to help sort of promote the consumer space, there are chunks of spectrum that are available basically for anybody to use. The main ones here are the 900 megahertz band, 2.4 gigahertz, and then 5 gigahertz. And then most recently here, 6 gigahertz, which we'll talk about towards the end of today's presentation. So basically anything that wants to use basically wireless radio communication has to operate in one of these 3 bands. So that means you're sharing that space with a lot of different devices from different manufacturers. Some will be Wi-Fi, some will be Bluetooth, some will be something completely different. There's lots of proprietary wireless protocols and stuff that are out there. So the next thing to talk about is if you're looking at data sheets. Well, let's put it this way. Let's back up. If you're looking at consumer products in general, you will see oftentimes the power of your Wi-Fi device marketed in the terms of milliwatt. So it was a really big deal back in the day when home routers started using 200 milliwatt radios. Before that, everything was 100 milliwatt radio. So it gave you a great marketing strategy, right? 200 milliwatts is double 100 milliwatts. So you're getting just huge, great range. And of course, today a lot of stuff is well in excess of 200 milliwatts. But back in the day, that was the big advertising push, and that's kind of why you find consumer equipment using milliwatts. Whereas when you look at data sheets for business class products, you will normally see the signal strength given as dBm, which is the scientific notation for measuring the strength of a radio signal, dBi and dBm. So dBm is what's being broadcast. dBi is the gain from or loss from any connected antennas, cables, things like that. So what you see is if you look at dBm, going from 100 milliwatts, that's 20 dBm, versus 200 milliwatts, which is 23 dBm. So you can see why from an advertising perspective, you would want to focus on milliwatts, because 200 versus 100 seems much more impressive than 23 dBm versus 20 dBm. So that's why you see the split now on the data sheet. So you say, well, why doesn't everybody just switch to using milliwatts? And the reason for that is because with dBm, it becomes really easy for you to calculate the total broadcast strength of a signal coming out of your device. So in addition to the power coming out of the chip, it goes through amplifiers, it goes through various connectors, cables, and antennas, and those all use dBm or dBi, and you can simply add and subtract those. So in the early days of Wi-Fi, I realize today most people don't do this unless you're really focused on outdoor point-to-point links. But in the old days, when you were creating point-to-point links and stuff, you would actually sit and try to calculate, exactly what the power was that was coming out of your device, and also for government regulation to make sure you comply with government limits on power output. You need to do that by doing, measuring all those different components. So by using dBm, that makes it much easier and simpler for you to be able to calculate that. So moving on here, a term that I put a lot of emphasis on that most people are not aware of or are vaguely aware of is signal to noise ratio. And that's simply the ratio of the signal that you want to hear, that data that's being sent that you want to be able to hear and capture, versus any other RF noise. Ambient noise, noise coming out of industrial equipment, or just other devices that are sharing that same spectrum and operating on those same channels at the same time. So that signal to noise ratio is really what tells you how good of a Wi-Fi connection you have, and is really what determines how fast your Wi-Fi connection is. So basically, that is the key to telling you in general how good your performance is going to be. It doesn't matter if you've got a nice healthy signal. If there's a bunch of noise that's hurting that signal to noise ratio, your devices will have issues or will intentionally slow down to be able to help deal with that signal to noise ratio issue. So that's something that people tend to overlook, which is a big factor when it comes to the performance and the quality of the user experience when using Wi-Fi. And then another term here is just attenuation. So people just need to understand that your Wi-Fi signal drops pretty rapidly as you get from where it's being transmitted from. So that's attenuation, basically how much that signal drops as it passes through different mediums. So with dry air, it'll go farther than, for say, with moist air. Moist air has more density. It will have more attenuation of the signal. Going through walls, you'll have more attenuation. Trying to penetrate a piece of metal, you'll have a lot more attenuation. So we've got this slide here. So up here is if you are trying to calculate your, how much your signal is going to lose based on distance between where you're sending the signal and where it's going. Here is that formula that you would use. As you can see, it is not an easy formula to memorize and calculate in your head. If for some reason you're doing outdoor point-to-point links and you want this, there are a number of free calculators available on the internet where you can punch in the dBm of your chip, the dBi of your antennas. Oftentimes, some of those ones will let you have put maps in so it can take into account obstructions, elevation changes, things like that, to be able to calculate for you that path loss. But if you want to do it yourself, here's the formula. So then the second part here is this big table, and this is just showing you in general how much of a dB loss different types of materials will have, and how much effective range hit you're going to have. So you can see here just a simple window can give you a 3 dB loss in your signal, right? And again, 3 dB is essentially having the power output, and it'll drop your range to around 70% of what it would be in open air. A tinted window, you can see, can more than double how much loss you're going to have, because most of those tinted windows have metal across that glass, and that's going to reflect more of the signal. And you can see you can get up to a 50% range hit on that. And then just different wall materials. Basically, the more dense the material is, the more loss you're going to have. So next up, let's talk a little bit about Wi-Fi range. So figuring out what your Wi-Fi range is, not simple. We always get these questions. Okay, if I buy your access point, what's the range? And really, there's so many different things that go into determining your Wi-Fi range. Like I said, there are calculators on the internet where you can type in all sorts of technical details to figure out, but in theory, you're going to be able to see. But it's a mixture, of the signal strength, the signal to noise ratio, the frequencies being used, etc. Now, the one thing people tend to overlook is that Wi-Fi is two-way communication. It's just like me talking to you if we were both in a room somewhere. So if my voice was doing good and I can talk loudly, and your voice, maybe you've got a cold, you can't speak as loud, then we have to be closer together to have a conversation, because it doesn't matter how loud I can talk if I can't hear what you're saying as a reply. And it's the same thing with Wi-Fi. It's perfectly normal these days for an access point to have 500 milliwatts of power. Very powerful, can send that signal very far, but it's also very common that the client device it's talking to is a mobile phone or a tablet, where the power output may only be 8 or somewhere between 8 and 25 milliwatts. So there's a huge lopsidedness when it comes to how much power is coming out of your device and how far that signal can go. So generally, it's not your AP that's determining your range. It's your client devices and their ability to get that signal back to your access point. If your access point can't hear the client device, you can't have a conversation. You cannot have communication. And, using networking protocols is two-way communication. Even when you are downloading, your client device still has to tell the access point in the internet, which file you want to download. It has to respond and tell the device, yes, I've received your packets, send me the next ones, or what, your packets didn't come through right, please retransmit them. So it's always two-way communication, even if you're doing something like downloading or streaming. And this is something that causes a very common problem we run into out in the field, which is you're doing a deployment at a hotel or an office building. You go out there and you try to figure out, your range coverage issues, or you have your customers, after you've deployed the network, calling and saying, hey, look, I'm having problems with your Wi-Fi network. Something is wrong here. And very often what it is they're using a mobile device, and the mobile device says the signal is fine. It says, hey, I've got 3 out of 5 bars. This is a good signal. And yet the Wi-Fi isn't working or is working poorly. And what's going on there usually is that your client device only knows the signal strength coming from your access point. It doesn't know its own signal strength at the access point level. So because of this real disparity in the signal output power, you often have devices, mobile devices, thinking they've got a decent signal when the access point isn't able to hear what they're transmitting back, and that screws up the connection. So that's something that's very often overlooked. Now, one of the things people will say, well, if that's the case, why don't I lower the power of the access point? Why are we pushing so much power into the access point? And the answer for that is that most usage is going to be downloading. Your client device is downloading data that's coming from your access point. And as I mentioned a few slides back, signal to noise ratio really determines how reliable and how fast your Wi-Fi connection is. So you're generally not uploading a lot of data from your mobile devices. So they don't need to be able to send data back quickly, but they would like to be able to download data very, very quickly. So by increasing the power at the access point, you increase your signal to noise ratio and you get a faster, better quality connection. So that's why access points or routers are generally much more powerful than your mobile device, and why you want it to be that way. So now we'll move on here to some just RF behavior. So, radio waves are invisible, but they do interact with the environment. Now we refer to radio waves as waves, and it is a good analogy to look at waves in, for instance, water, and it gives you a lot of the same behavior that we see with radio waves when they interact with the environment. So for a lot of what's going on, you can just imagine what happens when you throw a rock into a pond and you watch the waves that ripple out. Wi-Fi works very similar to that. Wi-Fi waves can reflect off of surfaces. They can hit an obstruction and scatter, generating, taking that one strong wave and breaking it into smaller waves radiating out in different directions. The signals can wrap around physical obstructions, something you do see with water waves. Now, one thing radio waves do that water waves can't do is they can penetrate through solid objects. But obviously they get diffracted and you get some extra attenuation, but it's very similar to what we see there. So that's also something that comes in when we're, troubleshooting an actual environment. Is oftentimes we'll find in environments where there's a lot of metal. So metal is going to both block signal and reflect signals. You get a lot of reflections and things like that. So what becomes one wave can turn into different waves coming from different directions and slightly different times on each other. And we call that behavior multipath, where the wave takes multiple paths to get to the device that's trying to listen to it, creating a sort of echo-like effect as far as the signal that the receiver is trying to hear. And that'll come back in a few slides here. Another problem we have with Wi-Fi, at least pre-Wi-Fi 6, is that, as I said earlier, Wi-Fi was created all the way back in 1997. And while it has gotten faster, the core functionality has never really been changed or modified. And that's largely due to backwards compatibility. And a lot of that's just because, we use Wi-Fi now for so much more than it was originally envisioned for, right? No one thought we would have 30 or more devices in our home that might be connected to the Wi-Fi at the same time with smart plugs and things like that. No one thought we'd be streaming high definition movies over them, etc. So it wasn't really designed for the idea that you would have a very busy, very crowded wireless network. So, excuse me. One thing I failed to mention earlier when talking about radio waves is with radio waves in general, devices have to take turns broadcasting. So one device broadcasts and then if another device wants to broadcast, it has to wait until there is an opening for it to be able to broadcast. Now, an analogy of this is for those of you that have ever gone on a road trip. In the days when we actually listened to the radio, you'd have the radio on and you would at some point on this long road trip get to a situation where the station, let's say you were listening to, 101.1 out of Los Angeles, but there's also a 101.3 broadcasting out of Fresno. So as you go up over the grapevine, you've now got two signals. They're not technically at the same channel, but they're close enough that there's bleed over, and you just get garbled mess. It becomes unlistenable. And that's what happens with Wi-Fi if you have two devices broadcasting at the same time. We call that co-channel interference. So back in the early days of Wi-Fi, the way they determined whose turn it was to broadcast was this very simple algorithm here, which is basically, do I have data to broadcast? Yes. Then I what they call sense the medium. Basically, I stop, listen. Is anybody else broadcasting? I don't hear anyone broadcasting, so I'll go ahead and transmit. Or if I do hear somebody broadcasting, I'll then wait a random amount of time and start the process over again. So it's fine when you've got a, network that isn't being used too much, or where you're sending traffic where it doesn't matter what order the pixels come, or not pixels, the packets come in, right? It worked fine for that. It doesn't work when you start overloading the network and having a lot of busy users streaming, a video nonstop, for instance, or if you're doing something like voice over Wi-Fi, which doesn't use any bandwidth, but it is very sensitive to packets coming in out of order or packets needing to be rebroadcast, because it's a basically a real-time communication, and there is no time to buffer and reorder those packets and solve those issues like we would with streaming. So voice over Wi-Fi is really sensitive to this. But this is how it works. So oftentimes what happens is you'll have a lot of devices on your network. Two or more will decide, hey, I need to transmit something. They'll end up listening to see if anyone else is transmitting at the exact same time, not hear anything, and then you'll have multiple devices decide to broadcast at the same time, and you get a collision and drop packets. So this is a very common problem. And as I said, with Wi-Fi 6, there are now addressed at least some of this to make this better, but it does require all of your devices be Wi-Fi 6 devices. Your older devices obviously are still using this old inefficient algorithm. So another problem we run into with this algorithm is something here we call the hidden node problem. And what it is it has to do here, we've got an access point, it's got this blue area is its range. We've got two different client devices who want to be able to transmit and talk to the access point. The problem we run into here, hence the hidden node problem, is that these laptops in this case are not within range of each other. They are unable to hear if the other one is transmitting. So they will never know that the other one is transmitting when they want to transmit. And you end up in a situation where both transmit at the same time. The access point is within range of both, so it will end up getting both signals at the same time, and it'll end up dropping the packets because it'll come through as a garbled mess as those two signals combine and interfere with each other. Now, another thing I want to address here is data rate versus throughput. This is something, if you've ever read Amazon reviews, you've encountered this. If you've done a lot of Wi-Fi deployments, I'm sure you've encountered this as well, which is, hey, this device says it's an AC 3000 device. I should get 3 gigs of throughput, but I did a test and I'm only getting 1.5 or some other number like that, which is significantly less than what's on the box or what's on the Amazon listing. So why is that? And this is what we're going to talk here about the terms data rate versus throughput. Now, these are terms that can be used many different ways. I am using them the way you, or at least from my experience, you most often see them being used out in the real world. So data rate is a measurement of the data that's being transmitted between two devices, whether they're physically linked together or wireless devices. So this includes the data you want to send and any additional overhead that's required to make that work, right? TCP/IP has additional overhead as part of the TCP/IP protocol, which has to be taken into account, etc. Throughput, as most people, I see it, colloquially used, is something people measure with an app like, or a website like, Ookla, speedtest.net, various software-based, data throughput testing things. And what that does is that takes a file and either sends or downloads it from another place and measures how long that's going to take. So it only sees the amount of data that it wants to send. It doesn't see any of the overhead. So because of that, you will get a difference between these two speeds, between the advertised data rate that you see on the data sheet and the throughput as you're able to measure it, because your throughput testing doesn't take into account overhead. Now, when it comes to Ethernet, it's generally not that big of a deal because with Ethernet, there's basically no overhead for using Ethernet besides the protocol overhead. Wi-Fi is a completely different story, and that's why you see these big discrepancies between the data rate and the throughput when you do some of your own testing. So there is a lot of overhead that goes into allowing Wi-Fi to work, right? You're using radio waves to send data in an environment where there are other sources of interference and noise that can cause packet loss, can corrupt data, etc. So because of that, there's all sorts of handshaking and checksums and things going on in the Wi-Fi protocol to make sure that doesn't interfere with your data and the data that's being transmitted is the same as what's being received. And it can easily add 50% or more overhead. So now you have a huge difference between your data rate and your throughput. It is just a general rule of thumb. You want to target, you expect to see somewhere between 40 to 60% throughput versus your data rate in the real world. Now, there are also some other issues that come into this, right? In addition, that's assuming that you've got a perfect Wi-Fi connection, strong signal, et cetera, but you do run into other issues which cause these tests to look even worse. For instance, and we'll get to it in the next few slides here when we talk about increasing speed, but your access point may be broadcasting for spatial streams, but your client device may only support one or two. So you're only going to be able to have, for instance, if your AP supports 4, but your client device only supports 2, your maximum throughput that client device that you're testing with can achieve just by itself is going to automatically have the throughput before we even start worrying about protocol overheads and things like that. And there are various other environmental issues which can degrade your performance when you're doing these Wi-Fi tests that people forget to take into account. So that leads us into, how do I increase speed? Now, this is not about how do you do it necessarily out in the field. It's how does Wi-Fi do it in general? How do we get faster speeds? And there's primarily been 3 ways that we do that when it comes to the technology. So every time we have a jump from G to N to AC, we're generally improving one or all of these 3 categories is how we're achieving, I'd say 90 to 99% of the speed differences between the different technologies. So one of those is encoding. Basically, how do you take that data and convert it into radio waves? So the more complex the encoding, the more data you can cram into the same amount of radio waves, but it also requires more horsepower and more energy to be able to do these complex calculations and conversions. So, that's why, it's taken all this time to go from 64 QAM with 11N to 1024 with Wi-Fi 6, is because you needed the technology to get to the point where the chips are not only available at your router and AP that can do this, but are energy efficient and can fit inside your phone or a cheap, $49 Walmart tablet. So that's why, it takes time for these different increases in coding to hit the market. The next one we do is something called spatial streams. We increase the number of spatial streams, and I will explain spatial streams in a few slides here for you. And then lastly here, we have increasing the bandwidth that we are using. How much bandwidth are we transmitting with at a time? So 11G, 11A, 11B use 20 megahertz channels. 11N doubled that to 40 megahertz. And now we're up to all the way up to 160 megahertz channels. So we'll go through it a little bit. We'll start here with channels because that's one of the areas that gets the most confusion. So this is looking at 2.4 gigahertz spectrum. Here in the United States, we have 11 channels that you can choose from, in theory, to use for your 2.4 device. This is roughly 60 megahertz of spectrum that's available in the US for unlicensed use in 2.4. Now, the problem we run into, though, right, is as I was mentioning, 802.11 ABG use 20 megahertz channels. So these Wi-Fi channels as defined are not spaced out 20 megahertz apart. I think it's closer to 5 megahertz apart. So what you get is you actually only get 3 channels that are usable, 1, 6, and 11, that don't interfere with each other. So as soon as you try to use more than 3 devices using 2.4 gigahertz, you will have overlap and start causing interference issues, or if you don't properly space out your channels. Now, you might remember here with 11N, we increased the bandwidth to 40 megahertz. But of course, the problem we run into is, again, there's only 60 megahertz roughly that's available for all 2.4 users to share amongst themselves. So if you've got one device using 40, you've only got 20 left over for everyone else. And the way 40 megahertz works in general is that it basically sits here in the center here in the US. In Europe, they can shift it over a little bit more because in Europe, they've got 2 extra channels. But here in the US, we're basically stuck here where the 40 megahertz channel sits in the middle. So no matter what, any additional 2.4 Wi-Fi device is going to have overlap and cause some interference between the two. That was why there was a big push in the later days of 11N to 5 gigahertz, right? So 5 gigahertz, it's a higher frequency, so the range is less. But look at this, you've got something like 25, 26 20 megahertz channels to use versus 3. So it made, that was why there was such a big push, right? It solves these interference issues that we run into with apartment buildings and condos and office buildings where you've got a lot of devices in the same area. It allows you to increase your bandwidth and still not have to worry about overlap, or does it? So one of the things you will notice here is there's this big chunk of spectrum that's highlighted in yellowy, orange, peach colored area here. And this is something called DFS channels. So we need to talk about those. So DFS channels is something that came about because this 5 gigahertz spectrum that was opened up for unlicensed use used to be licensed use only. And when the FCC decided to open this up for everybody, we ran into an issue, and that is the legacy users are still using it. And we've got a lot of infrastructure built on top of the idea that this was licensed, restricted spectrum. And now you're letting in a bunch of people to just use it wherever you want. It's like you live in your, your gated community, and one day they tear down the gates and turn everyone's lawns into a park for anybody to use. So it's sort of the same thing. So the way the FCC said, hey, look, we don't want these people, these dirty, filthy, unlicensed spectrum users to interfere with our licensed legacy customers. So if you want to use these 5 gigahertz channels that were already being used, you have to do this thing called DFS. And basically what DFS says is before you broadcast on a specific DFS channel, you must first verify there are no legacy users using that channel. Once you've verified there are no legacy users using that channel, you can start broadcasting on it. But if at any point you detect a legacy user or what you think may be a legacy user, you have to stop broadcasting. So that causes some issues for people. The first one being you may at any point be randomly disconnected from your 5 gigahertz connection if you're using one of these DFS channels. And it may take a little bit of time before that AP or device changes channels and starts broadcasting again, right? Because if it's a DFS channel, you have to stop broadcasting, decide which channel you're going to switch to. And if that channel is also a DFS channel, then you've got to pause and verify no legacy devices are using it before you can allow everyone to use it again. So there are reliability issues because of that. Obviously, some users based on the application may not be able to tolerate a brief disconnection. The other issue you run into on this is that it adds about 6 months to the FCC certification process last time I checked. So especially in the consumer space where everyone's trying to be first to market, a lot of consumer devices don't support DFS. One of the biggest ones that has issues with DFS is a little device that you may have heard of called an iPhone. So for whatever reason, a lot of the iPhones do not support DFS. So for those two reasons, a lot of you out there have decided, I don't want to support DFS channels because it causes my customers to complain, because when they're bringing their own device from home, it can't connect to some of the access points depending on where they are in the building. And because my users are complaining that they were temporarily thrown off a voice call or something like that using Wi-Fi. So now if you eliminate those DFS channels, you go from like 26 non-overlapping channels to 8 or 9, depending on where you are in the world. So it makes a big hit there, right? That takes a huge chunk of that available spectrum away from you from a practical standpoint. So then we decided, right, to get faster speeds, we double the bandwidth, hence we double the speed because we can send twice as much data at the same time. Well, now you're down to just 4 non-overlapping channels. You're almost in the same situation you originally were in 2.4, which is why you wanted to move to 5. And again, as time has gone on, we've gone faster, 80 megahertz channels. So again, you switch to that, you want to maximize, right? You want to run your AP at full speed. You've only got 2 non-overlapping channels you can use. And then with the latest 11AC Wave 2 and Wi-Fi 6 and 6E devices, we're using 160 megahertz channels. So those have to use DFS. So you will run into issues absolutely out there where you have a consumer device that is, Wi-Fi 6 or says it is, but it may not support 160 megahertz channels. Some of your access points or routers may not support 160 megahertz channels because a lot of you, especially in the business world, don't want to use them because of the issues using DFS brings. So something to keep in mind, when you're looking and comparing speeds, the use of 160 megahertz channels is a good example of this. We do have devices right now. We just launched the NWA 90 Pro versus the NWA 90. Both support 2 spatial streams. And again, we'll get to spatial streams. We're almost there. But one's twice as fast as the other. And it's because the Pro supports these 160 megahertz channels, where the non-Pro version only supports 80 megahertz channels. So now finally, spatial streams. As I was mentioning before, your Wi-Fi signal gets transmitted and it reflects off of things, creating this thing called multipath, where your data can take multiple paths simultaneously to get to your device that's trying to receive them. And because those paths are different lengths, you get a sort of distortion or echo type effect, right? You're in a big room, big empty room, and you shout and you'll get an echo. It's the same sort of thing. So this used to be the bane of the existence of Wi-Fi in the 802.11b in the early end days. People who were smart, though, figured out there's a way to actually take advantage of this. So you can take advantage of this, the fact that signals are going to bounce off of and take slightly different paths, by taking advantage of multiple antennas in your device. They are physically separated from each other. They may have slightly different antenna patterns, and that causes those signals to take different paths. So what happens is instead of using, transmitting one, we'll say a 20 megahertz bandwidth signal, you can send 2 streams of data using that same 20 megahertz of space. And if you had, say, 2 streams or 2 sets of antennas, that's what we did here. So this is what we call MIMO, multiple in, multiple out. The ability to be able to transmit multiple out, multiple signals simultaneously using the same channel, and then multiple in your receiving device to be able to hear and differentiate those signals, even though they're on the same channel, same frequency, and be able to combine them together. So what you would get here with 11N and 2.4 gigahertz and 11AC is each one of these spatial streams can be 150 megabits. So an N300 device told you it had 2 spatial streams, right? It could have 2 different 150 megahertz streams, which combined together to 300 megahertz. If you had an N450 product, it told you had 3 spatial streams. Then with 11AC Wave 2, we introduced MU-MIMO. So still multiple in, multiple out, but the new MU stands for multiple user MIMO. It's the exact same idea, using these spatial streams to allow you to transmit different sets of data simultaneously on the same channel. But instead of combining it together like before into one 300 megabit stream, we now have the ability for your access point to transmit 150 megahertz per spatial stream to one user and another 150 megabits per spatial stream to a separate user. So the aggregate bandwidth is still 300, but now it's split between 2 users. And then with Wi-Fi 6, they've added what they have the ability to do what we call upstream or uplink MU-MIMO, which is the ability not only for the access point to take advantage of MU-MIMO and transmitting, but to allow client devices to simultaneously be able to transmit back to the access point without interfering with each other. So when you are looking at the data sheets, particularly for business class equipment, you will see things marked as the 2x2, 3x3, etc. So that's telling you how many spatial streams that device supports. So the first one, I believe, is for transmit, and the second number is for receive. So if you see 2x2, it tells you this device can transmit 2 spatial streams. It can receive 2 spatial streams. If you see 3x3, it can transmit 3, it can receive 3. What we run into though, and that's what you would generally see on most of your access points or routers. They're generally 2x2, 3x3, 4x4. They're synchronous between the two. But when you look at client devices, it's often asynchronous. You will see a 1x2 or a 2x3. So basically that's telling you, again, that first number is transmit, the second number is receive. So it's telling you as a client device, I can receive at more data than I can then send back to the access point. And why? Because it's cheaper, uses less power, right? You're not having to encode as much data, which is a big battery hit. But also, again, in general, your client devices are downloading a lot more than they're uploading. So it's more important to have fast download than fast upload. So you see that a lot. Another thing you will see is, I don't know if you can see it there on the text, but it's a number 4x4 in this case. There's a colon and then the number 3. So what does that mean? That's telling you that this device can transmit 4 streams, can receive 4 streams. Just kidding, it can only do 3. So that number after the colon is telling you how many streams it can actually handle simultaneously. And now those front 2 numbers are telling you how many options they have. So you only use 3, but it can choose from those 4 which 3 to use. And in theory, that may help with directing the signal or things like that. But in general, a 4x4:3 should be treated the same as a 3x3. And you do see that now with our NWA Pro. It is, I believe, 3x3:2. So it's only 2 spatial streams, but in theory, there's 3 sets of antennas, and they can use any 2 at any one time. So to put it all together, you combine all 3 of those things to figure out the maximum speed your device can handle. So you can see here, you've got spatial streams, modulation type, and then how much bandwidth we'll be able to use. So on a lot of AC equipment on the 2.4 radio, the maximum speed is 866. You'll see that on the data sheet, and it's normally rounded up to 900 when you're adding it to your 5 gigahertz radio. So that's assuming you're using a 160 megahertz channel. That's assuming you can handle 256 QAM. And that's per spatial stream, right? So if you add a second spatial stream, you essentially double it to 1733 here. But if your signal to noise ratio is poor, you may have to drop from 256 QAM to 64 QAM. So that'll drop you from 866 to 650. And maybe you don't want to use DFS channels. So now that'll drop you to 325 megabits maximum throughput. So the combination of these 3 things determines the maximum data rate that you're going to see on your wireless network for that specific equipment. Now, the next question we get a lot is, how many devices can I stick on this access point? And the short answer is, there is no difference. It doesn't matter which access point you're looking at. It's the same. So you'll say, Sean, you're lying to me because I'm looking at data sheets. And this device here says it supports 256 clients. And this other guy's data sheet over here says it supports 1,024. Why are you lying to me? And the answer is, what you see on the data sheet is basically how many entries in the memory and in the database that your access point or router has, how many entries it can support for client devices. But realistically, you're never going to get close to that because of all the problems we were talking about before, which is as you add more users and you add more demanding users, there's not enough available airtime for everybody to take turns broadcasting. So that generally, your users are going to cap out and start experiencing significant performance complaints long before they get anywhere close to whatever number is on that data sheet, because that number that's on that data sheet doesn't affect the issue that we run into. The issue we're running into, or the limitation we're running into, is the available airtime that all of those users have to share. And that is the same no matter how cheap or how expensive of an access point you are using. So it's all going to come down to what type of wireless users you have and what they're doing on that network. And so, so again, if you're doing something like voice, which can't buffer because then it delays things too much, you may have a much lower number of users that you want to allow per access point than if you're, say, people are just streaming Netflix. Even though Netflix is using more bandwidth and more airtime because of buffering, it may not be an issue as quickly as it is with your voice users who are using almost no airtime. So it just depends what's going on that network. But assuming you have active users, you will never get to whatever numbers on that data sheet for maximum number of users before basically the network breaks down and everyone's complaining. So here's an example. We're using this example here. It's a hypothetical. We've got an access point here. It can support 3 spatial streams. And it's got wireless clients connecting to it. And we'll just assume all of them are using 5 gigahertz radio, 20 megahertz channels, and signal strength is 67 dBm. So how many users can get on there? And in this scenario, each of these wireless users is trying to stream a video, and this video is encoded at 3 megabits per second. So in the first situation here, we're using a laptop, and this laptop supports 3 spatial streams. We're able to get 34 laptops onto that access point before we start running into issues. Aggregated throughput's roughly 100 megabits per second aggregated throughput in this example. If we take away these laptops and replace them with tablets, same signal strength that they can broadcast from, but they only support 2 spatial streams. Now we can only have 21 devices on that network before we start running into issues due to airtime. So that gets us down to about 65 megabits aggregated throughput. Again, nothing else has changed. And of course, in the real world, there'd be all sorts of different things, right? Different signal strengths, different signal to noise ratios due to the, how far away the clients are from each other and from the access point, et cetera. So the only thing that's changed is just the spatial streams. Switch it to a little cheapo $99, cordless phone or mobile phone. It only supports 1 spatial stream. So now you can only get 10 users on that same access point, on that same wireless network before you start running into issues. And in this case, the aggregated throughputs are roughly 30 megabits per second. So again, that's just changing one factor onto your network to determine how many users you can really get on there before you start getting into issues. And again, in the real world, it gets a lot more complicated very quickly. So something I've been talking about, I've mentioned before, is code channel interference. So this is that issue we run into, which is that in general, ignoring MU-MIMO, but in general, only one device can be using the same frequency at a time. They have to take turns sharing that thing. And if you have other devices using the same frequency, you get these interference. So that's code channel interference. Multiple devices broadcasting using the same frequency at the same time. So as we talked about before, the way historically we dealt with code channel interference is we would turn down the signal strength on our access points. And we do still recommend you do this in certain situations. But one of the issues you have when you turn down the power is your signal to noise ratio gets worse. So you're getting rid of code channel interference, but you may also be causing worse signal to noise ratio and thereby slower performance. So it's a trade-off, which in your particular environment out there, which is going to work best for you? Do you want to just have to eat the code channel interference, or do you want to deal with worse signal to noise ratio? So one of the technologies that's been designed to address this is called smart antenna technology, and this is available on 3 or 4 of our access points right now. And so what this does is, instead of having one antenna in there, it's got a special smart antenna that has the ability to basically emulate hundreds of different antenna configurations. And it can roughly in real time choose different antenna patterns based on the client it's trying to communicate with and where that client is in relation to the access point. Now, this technology does not require anything special on the client device. It'll work with any client device. It's all done at the AP level. Now, something we've spent a lot of time doing versus some of the other vendors that have smart antenna is we've really focused on dealing also with this code channel interference issue. So we'll not only create an antenna pattern that focuses the beam to the client device, but we will also try to avoid other sources of interference that may cause problems with that Wi-Fi connection. And unlike something like beamforming, smart antenna works with mobile devices. It doesn't require them to be roughly stationary to take advantage of it. It works even if you're walking around talking on your phone. So I want to give you a real world example. This is a real test that we did. This is, I believe it was a hotel that they tested this in. It's a 2-story hotel, story 1, story 2. We've got a bunch of our NWA 1302s, basically roughly the same as our current WAC 500H, but with smart antenna. And they deployed 5 gigahertz radios in each guest room. which is very common these days. And we'll talk more about that towards the end of today's presentation. And as you can see, no APs are directly next to each other using the same channel, but we've got a limited number of channels that we can use here that don't overlap using the 5 gigahertz radio. So that's what we've done here. We were avoiding those DFS channels. So we took our product and we took a Ubiquiti product and we tested them. So with just one access point going here, we were able to achieve a little over 400 megabits aggregated throughput, both on our device and on the Ubiquiti access point. In fact, they beat us. They were just a little bit faster than we were. Airtime utilization was roughly 67%. And again, generally, most networks get up to around the 75% utilization before you start running into some issues. So if you see channel utilizations at 75% or higher, you've probably got some users that are unhappy with you. So we did the test, but this time with 2 access points turned on. Again, they're not next to each other. In fact, one is on a completely different floor, and reran the tests. And you see here, our access point with smart antenna was able to achieve an aggregated throughput of 785 megabits per second between those 2 access points. On the Ubiquiti side of things, aggregated throughput was 555 megabits per second because they don't have our smart antenna technology. They just have your standard stationary antenna configuration. And if you look here on your channel efficiency, you'll see with the Ubiquiti with 2 APs, they were able to achieve 95% airtime utilization, where our smart antenna allowed us to get 131% airtime utilization between those 2 access points. So we were able to basically exceed the theoretical maximum because by using smart antenna, we were able to allow those access points and their clients to talk simultaneously without interfering with each other, where the Ubiquiti with a standard antenna wasn't able to do that. You'll also notice here, the aggregated throughput per AP is roughly equivalent between the two, where with Ubiquiti, one AP was half the speed of the other. So now we do that same test, and we do it with 3 APs. And we see the same similar behavior. The Zyxel AP was now able to get over 900 megabits aggregated throughput and increase airtime utilization to 155%. Whereas Ubiquiti actually had a hit. They dropped down to 91% because of just the interference issues between these different APs fighting for that airtime. But you'll also notice here, each of those APs was able to roughly have 300 megabits throughput. Where with Ubiquiti, it was again widely disparaged speeds between those different access points as they and their users fought for that little limited airtime utilization. So that's what smart antenna does for you. So that's why if you're doing something like a school or you're doing a really dense, hotel or conference room or thing like that, it makes a lot of sense to use smart antenna. It will save you a lot of headaches and make your users a lot happier with what's going on. So now there is another technology here that we offer on our access points, and I think we're the only guys that offer this. Feel free to send something in. I see someone's got their hand raised. So again, if you have a question, send it in using question and answer, and I will respond to what gets sent in using the question and answer in Zoom. So just going on while I wait to see if that question gets written up and sent in. So traditionally, again, your access points have one fixed antenna pattern, and it's designed with the idea that you're going to mount the access point on the ceiling above the area to be covered. And it roughly creates an umbrella shape as it radiates up, out and down, covering the area below it. The problem is, in the real world, you don't always get to mount your access points directly above the area to be covered. Sometimes you get stuck having to mount them on a wall. So the problem is, though, that your antenna is configured to be able to cover everything below it. It's not really designed to cover things shooting out in front of it a long distance. So you end up sending a lot of your signal up into the floor, down into the ceiling, or depending on construction, you're either wasting a lot of signal or you're causing interference with devices on the other floor. So what we have here is something called dual optimized antenna. So we have 2 sets of antennas in these access points, and these are the access points that generally end in the letter D. And what that means is they've got dual optimized antenna. So you can choose, depending on where you mount that particular AP, whether you want to use the ceiling mount type installation or a wall mount. So it will change the antenna pattern based on where you have mounted that device to optimize based on where you've installed it. So now just some general rules here for you as to, where you want to mount your access point. So a general rule is you want to mount it above the area that's going to be covered. And in general, you want to mount it higher, the better. And the reason why you want it higher is because you're trying to minimize the amount of obstructions that signal has to go through. You want it to be able to have as direct a connection as possible between the client device and your access point without that signal having to pass through people, cubicles, desks, office furniture, etc. So you want it to be as much open air as possible between those two with no obstructions. Again, so within reason. So when it comes to drop ceilings, most, I think, office buildings these days have a drop ceiling, which is you've got a true ceiling and then you've got those acoustic tiles that are hanging, anywhere from 3 feet to 6 feet or more below that true ceiling, covering up all the pipes and ductwork and things like that. So those drop ceilings generally have very little signal attenuation. So rather than punching holes in those ceilings and running cables through them and stuff, oftentimes, provided your local building codes allow it, you can just simply rest the access point facing down on top of the drop ceiling rather than having to put it where everyone can see it and poke holes in the existing drop ceiling. So again, some building codes don't allow this. But if your building code does allow it, that's an option for you as well. And then just in general, if you're mounting on a true ceiling, keep in mind, you know, ductwork, conduit, things like that are metal, those are going to cause problems with your signal, right? The signal is going to hit those and bounce off of them. So in general, you want to, when you're positioning your access point up there, you want to avoid large metal objects. You can find them fairly easily if you search for them. They have standoffs that'll, basically a pole with a little flat bracket on the bottom that you can mount on the ceiling to be able to drop that area down below all those obstructions and then mount your access point to that pole. We don't sell them personally, but they are out there and I think they're pretty easy to find. So when it comes to hotels, specifically guest rooms in hotels, the traditional way we did Wi-Fi for the longest time was what we call umbrella. You would stick the access points usually out in a hallway, a common area, and it would cover anywhere from 4 to 16 rooms from one access point. So you just run them down the hall, however many spaces you need to go. You would do some site surveys to find out, what the building materials are and do it. So that's how traditionally hotels have been done. There are still hotels, particularly the lower end hotels, that still do it this way, but most newer hotels and most of your mid-tier and higher hotels are moving to instead doing a per room access point where you have one AP per room or one AP per maybe 2 rooms. So you mount it on the wall and it covers both rooms that share that wall. So why have we made the switch from the umbrella coverage to this? And it just comes down to the way people use Wi-Fi has changed. It used to be the only people that cared about Wi-Fi were business travelers, and they were wanting to get on their laptop to do work. And obviously now that's no longer the case. Everybody's got at least one mobile device with Wi-Fi in it. You may have more. You're not just sending emails and browsing the web. You want to be able to stream Netflix and Hulu and whatnot. So you've got a lot more users wanting to connect to that access point, and you've got a lot more utilization of those access points. So because of that, one access point may get overwhelmed when you're dealing with multiple rooms trying to be covered. So instead you use these smaller APs that generally have lower output power to avoid interference between rooms. And you put one of those in each room, or like I said, one for every other room. Now they have special access points that are specifically designed for that. In addition to having generally lower output power, ours have pass-through ports. And one of those pass-through ports can do PoE pass-through. So what you see in a lot of these new modern hotels is you'll run one Cat5 or Cat6 cable to the room. It gets PoE from the central office. That powers up the access point. And then you run cables from that to your VoIP phone. That provides your phone in the room, uses the PoE that's being passed through to power up the phone. You've got another cable that runs to the back of the TV for an IPTV signal. So now you've just run one cable to each room, and you can use that one cable to provide power and data connectivity for multiple devices in that room. And then just in general, if you are mounting standard access points in the room, turn off the LEDs. Most of our access points, we have the ability to do that in the GUI. Our hospitality aimed access points by default have those LEDs turned off. Just because people are trying to sleep, they're tired, they don't want to, have a flashing green or amber light going off in the corner or up on the ceiling where they're trying to sleep. Now let's talk a little bit about public areas. So when you're doing public areas, you want to take into consideration individual areas independent of each other. So, don't crowd the restaurant with the bar, with the lobby, with the pool and treat them as one area. Treat those as each individual areas and build your coverage based on those areas. Specifically, what you want to take into account is user density. The more users you have, the more access points you want in that area. When you're configuring load balancing and client steering, you want to create groups based on these physical areas. You don't want a user in the lobby trying to get load balance to an unused access point on the 5th floor in somebody's room. So you need to split those apart. And that is something we have run across many times out in the field where people just have one giant configuration. So everything's being load balanced across all APs. Now you need to do it per area to make it much more efficient. And if you have areas where you have a lot of users, use smart antenna. If you've got an expo center or a conference room, you may want to use smart antennas in those spaces so you can fit more users in there with less access points. Next up is schools. And schools is where I get the most pushback from people. And it's one of the areas where it's harder to just sort of make general rules for them, but I'm going to try. So the main thing, again, that you're looking at here is usually going to be user density. How many students are in each classroom? And then what are they using their Wi-Fi devices for? And this is really, really key because it does make a difference. There are some classrooms where every user's got a Chromebook. They're all connected to that Wi-Fi. And instead of, broadcasting a film on a projector, or instead of using some sort of projector to project the teacher's screen, they instead stream the video to those users, or the stream the teacher's desktop to those users to share the presentation. So instead of looking at a big billboard in the front of the room, everyone's looking at their own individual device. So if you've got a situation like that where you're using a lot of bandwidth, you may need to have multiple APs per classroom. Whereas traditionally, if the students are only using their mobile devices, maybe to submit, tests or something like that, or to browse the internet for research purposes towards the end of class, you may not need that. You may be able to get away with just one. But as a general rule, in a multimedia classroom, we suggest 2 or more APs if there's 20 students in the room, and use smart antenna if you've got 30 or more students in the room. Again, that may not be the case. It just depends on that individual school and classroom and how they are using that wireless network. So now let's talk a little bit about Wi-Fi 6. Now, the reason I split Wi-Fi 6 off from what we were discussing earlier about Wi-Fi is because Wi-Fi 6 really makes some significant changes to the underpinnings of Wi-Fi that solve a lot of those issues we were talking about earlier when it comes to 11AC, 11N, et cetera. Now, one thing to keep in mind with Wi-Fi 6 is your clients also need to be Wi-Fi 6 to take advantage of these benefits. And they need to support these features because not all Wi-Fi 6 devices support the same feature set, unfortunately. So some cool things about Wi-Fi 6. First one is it's designed to work on any frequency. So a lot of people don't realize it, but 11AC only improved the 5 gigahertz radio. If you've got an 11AC device, that 2.4 radio is still 11N. So with Wi-Fi 6, you can have Wi-Fi 6 now on your 2.4 and your 5 gigahertz radio. Wi-Fi 6 was specifically designed to sort of handle high density environments, whether we're talking number of users per access point or whether we're talking about number of access points in the area. It's been designed to solve a lot of those issues. And it does that by using OFDMA, bidirectional OFDMA, bidirectional MIMO, spatial frequency reuse, a number of other technologies there that we won't get into today. So there's some cool tech in there that makes this possible. Wi-Fi 6 was only, I think, finally approved in 2021. but there was products out before that. And a lot of the stuff based on earlier chips or just based on the cheaper chips are missing some of those features that are required there. The Wi-Fi Alliance, for instance, didn't require bidirectional MIMO until 2022, even though there were people selling those products back in 2020. And it was part of the standard. It was part of the standard in 2021, and yet the Wi-Fi Alliance ignored it until 2022. So because of that, a lot of products before 2022 don't support bidirectional MIMO, even though it's a big part of being able to cram more users into Wi-Fi 6, which makes Wi-Fi 6 special. So we've got an example here, just looking at the Qualcomm Gen 1 chip versus the Qualcomm Gen 2 chip. So again, it's missing bidirectional OFDMA, it's missing bidirectional MIMO, it's missing TWT and BSS coloring, and it cannot be upgraded and added to it. So you have to have a Gen 2 or better chip to support all of those features. So there are still products out there using these Gen 1 chips because they are cheap and they are missing some of those features. So when it comes to Zyxel, everything basically NWA 110 and higher is full Wi-Fi 6 feature-wise. Our 50 and 90 series are missing some of these features. Those are our cheapest, most inexpensive access points, but everything 110 and higher are true business class access points, all support the full Wi-Fi 6 feature set. Another thing to also keep in mind is some vendors are only putting Wi-Fi 6 on one radio. They're still putting Wi-Fi 4 on that 2.4 radio. Ubiquiti, for instance, has done this on some of their lower end APs. We put Wi-Fi 6 on both radios on every one of our Wi-Fi 6 APs. But something else to keep in mind when doing it, because I guarantee you, they don't call it out and say, Wi-Fi 6, but only on one radio. It's just, here's our Wi-Fi 6 access point. You figure out that it's only on one radio. So something to keep in mind when you're doing comparison shopping to look for. So now let's talk about Wi-Fi 6E. So Wi-Fi 6E really came out roughly last year, where the product started hitting the market. So this is basically Wi-Fi 6, but it can operate in the 6 gigahertz space. So basically what happened is the US and Europe opened up this 6 gigahertz spectrum that was already being used by licensed users and opened it up for everybody to use without a license. You might remember this story from DFS. So why did they do that? And the answer is because 6 gigahertz spectrum here is gigantic, right? We're talking about how we're getting faster and faster speeds by increasing the amount of bandwidth that's being used. So with the Wi-Fi 6, you've now got 7 non-overlapping 160 megahertz channels. You might remember with 5 gigahertz, we only had 2. With 2.4, we have none. This 6 gigahertz spectrum is bigger than 5 gigahertz and 2.4 combined together. So this is fantastic for those larger deployments where you've got a lot of users crammed into the same space. It's ideal for condos and apartments and things like that, in theory. So let's talk a little bit about it. So just like with DFS and 5 gigahertz, there's already people with licenses using this 6 gigahertz spectrum. The good news is it's primarily outdoor users. It's being used by utility companies, from smart meters to talk back to the office. It's being used by news reporters to send their video feeds up to the TV for live streaming, etc. So that's one issue we run into. There are these other users. You might remember the solution to that with 5 gigahertz was this DFS. Now almost no one uses DFS because of the issues it introduced. So for Wi-Fi 6E, the FCC came up with what is in theory a better solution. So now again, these legacy users are outdoor. So when it comes to indoor use, there's nothing special required. You can go hog wild with 6 gigahertz indoors, but you can't use it outdoors. So why is that? And will that change? And the answer is yes, that will change. The challenge you run into is for outdoor use. Rather than use DFS, which caused all these problems, the FCC came up with a new thing called automatic frequency control. Basically, it requires your access point or router, if it's being used outdoors, to communicate its location and channel usage with a central database. And that central database will check for legacy licensed users and make sure that they aren't in that area before it allows you to use that channel. The problem we've run into with this is this automatic frequency control still doesn't exist. So because of that, you can't use Wi-Fi 6E outdoors currently. The FCC, shoot, I'm forgetting if it was November last year. I think it was November last year, authorized a number of automated frequency controls third parties provisionally. So there is provisional support, basically a beta test of this thing. But until it comes out of beta test and everything and gets officially licensed and allowed for everybody to use, you really can't use outdoor 6 gigahertz. There may be some vendors that will provide their own automated frequency control that will put you into basically their beta test. But officially, there's no official solution that you can go out and buy currently for this to work with. So, and then on top of all of that, these legacy users have sued the FCC to block Wi-Fi 6E usage from unlicensed users. So that's going through the courts. We're still waiting for the FCC to fully certify some of these automated frequency control solutions. So we got to wait for at least this part to get done. And then we've got to figure out how to implement it into our access points. So it'll probably mean access points need to have a GPS to determine their location or some other location technology in them. They'll need to be able to communicate and be certified for these different third-party frequency control solutions. So short version is outdoor is coming at some point in the future, not today. Indoor is here today, go hog wild. But there are some other issues with using it indoors. The primary one here is range, right? As frequencies go up, the range drops. So that has been a problem if you go look at some of the Wi-Fi 6E device testing out there, whether we're talking consumer routers or business access points. There's a lot of complaints about this. Basically, you will need more access points to cover the same amount of area than you do currently with 5 gigahertz. So if your customer's upgrading from 5 to 6, you may need to completely remap and retest where you're going to deploy those access points so you have the proper coverage, because this signal does not like to go through solid walls. So you get less range, you might get some less speeds because of that. The other challenge we run into here is cost. So the cost, right? You've now got, in theory, up to 3 radios operating simultaneously in your access point. So you need a more expensive, more powerful CPU to be able to process all of that data. You probably need a faster Ethernet connection so it doesn't bottleneck that data. So generally, Wi-Fi 6E devices are going to be a little bit more expensive. Okay, so that's it for the bad news. And so as you're saying, what are the main use scenarios here? And the primary ones where you probably want 6E. Oh, of course, and also the other issue here is your client devices need to support 6 gigahertz, right? So you really only see today 6E support on phones, like high-end phones and high-end tablets, or excuse me, not high-end tablets, high-end, tablets and also laptops. So it's going to take a while for the technology to get cheap enough and a little bit more efficient on the electricity usage before you see it become widely supported in client devices. So that's something to keep in mind. So the main areas where you see benefit of this is high density areas. That's where it's designed for. High density, but also those who need those faster speeds. I don't know what those are, but if you need those faster speeds, 6 gigahertz Wi-Fi 6E is for you. A big area where we see 6E being used is for wireless backhaul. So wireless backhaul, you would use 2.4 and 5 to communicate with your existing users, and then you would use the 6 gigahertz radio to make a wireless backhaul connection to additional access points. So you don't have to run Ethernet to all of them. But of course, obviously, you still need to get them power somehow. But that is one area here for those looking to deploy mesh in a business environment. 6 gigahertz may make it reasonable to do using an external AC adapter rather than doing new drops, because it's using a separate radio. It won't slow down your 2.4 and 5 gigahertz users. I don't have a slide on it, but I do want to talk briefly about Wi-Fi 7. You will probably see, I think there may be some consumer stuff hitting the market now. Most business stuff will be towards the end of the year or next year. Wi-Fi 7 is just a continuation of 6E. And the primary thing that it does that I think most people would care about is it allows you to use for one connection, use 5 gigahertz and 6 gigahertz simultaneously. That's probably the coolest thing it does. But again, how long is it going to be before there are client devices that support it? And when are you going to get to the point where you have use case scenarios for it? But Wi-Fi 7 is coming. Like the primary thing is, again, 6 gigahertz and the ability to use 5 and 6 gigahertz simultaneously for a single user. Whereas right now, your client has to be either 5 or 6. In the future, in theory, you'll have 2 radios in that client device. You'll be able to simultaneously connect to both radios and then combine them together for even faster speeds. There's some other stuff in there, but it's that allows you maybe to access points to coordinate with each other. But that's really what it is. It's really about coordination and combining things together for even faster speeds. Otherwise, it's still roughly Wi-Fi 6 or 6E. And with that, guys, we are done. I know it's a long webinar. It's a dry webinar. I appreciate you guys sticking it out here to the end. If you have any questions, again, send them in using the question and answer interface in Zoom there, Q&A. I will respond to it while I wait for any questions, because none have been sent in yet. Just to highlight here for you, our webinars, most of them are recorded and uploaded to our YouTube page. The US office is on YouTube as Zyxel America channel. So that's where you will find any webinars you missed or had to leave. It's also where you will find advertisements, video case studies, guides for the best ways to do things, best practices, things like that. That's where you'll find them. And then if you want to connect with us, we're on LinkedIn as Zyxel US channel. That's us here in North America. And then lastly, we do have user forums at forum.zyxel.com. They are a great resource not only to talk to your fellow Zyxel users, but it is monitored by our tech support and product management team. They will occasionally answer questions on there. It's also where we often are the first places where we will post security bulletins, release notes, things like that. So go check it out. I don't have any questions that have been sent in, so I'm going to go ahead and end today's webinar. Thanks everybody for joining today. I hope to see you at one of our other future webinars. Thank you.